Most people believe the same thing about empty space. They believe it is empty, a vacuum, drained of everything, a region of pure absence, a true nothing. But here is what they were never told. There is no such place. Quantum physics tells us that even the emptiest patch of space, far from any star, swept clean of every atom and every ray of light, is not still. It hums, it jitters. Pairs of particles flicker into being out of the emptiness and vanish again, constantly, everywhere, in every cubic inch of the universe, including the space inside your own body. The uncertainty principle does not permit a perfect blank. It never has. And once you know that the emptiest possible nothing is secretly full of activity, a far stranger question opens up beneath your feet. If empty space was never truly empty, then what exactly did the universe come from? Get comfortable. Hit subscribe if you are new here. Because by the end of this, the word nothing will never sound the same to you again. Now, let us slowly ease into this. Part 1. The thing you cannot picture. Try something with me before we begin. Wherever you are right now, let your eyes close, or let them rest on some quiet patch of the room, and try to think of nothing. Not nothing in the loose, everyday way we use the word. The way you might say, there is nothing in the fridge, or nothing on television. Try to think of a real nothing, an absolute nothing. Most people, when they make this attempt, start by imagining a vacuum. They picture a region of space that has been swept perfectly clean, drained of every atom, every speck of dust, every flicker of light and heat. A box with the contents removed. A pocket of the universe with nothing left inside it. And that is a fine first step, but it is not yet the thing we are after, because that imagined box still has something in it. It still has space. It still has the 3 dimensions in which the box could exist, the volume that the emptiness fills, the distance from one imagined wall to the other, and it still has time, the quiet ticking that lets the emptiness simply sit there and continue to be empty. So go further. Take away the space. Take away the time. Try to think of a nothing that is not just empty, but is missing the stage itself, missing the very arena in which things and events could occur. No length, no duration, no here, no later. Not a dark room, because a room is a place. Not a silent moment, because a moment is a piece of time. If you found that your mind simply slid off the idea, the way a hand slides off wet glass, you are not failing at the exercise. You are succeeding at it. You have discovered something honest about the shape of your own imagination. Every picture you try to build still smuggles in a place to put it and a stretch of time for it to last. The mind cannot draw a nothing because the mind only knows how to draw somethings, and it always needs a canvas. The true nothing has no canvas. Notice, as well, the way the attempt keeps failing in the same particular direction. When you try to picture the absence of everything, what your mind tends to offer up is darkness, a black expanse, a great, unbroken dark, and it feels, for a moment, like you have arrived at the thing. But you have not. Darkness is not nothing. Darkness is a something. Darkness is a place that happens to have no light in it, and a place is exactly what we agreed to take away. The dark you are imagining still has width. It still has depth. It still has a direction you could, in principle, travel through it. It is a room with the lamp switched off, and a room is not nothing. A room is one of the most something things there is. The mind reaches for darkness because darkness is the emptiest picture it owns, and then it quietly hopes you will not notice that a picture, any picture at all, has already failed the assignment. This matters more than it might seem, and it will matter all the way to the end of this video. So let me say it once, slowly, and let it settle. The reason the true nothing is so hard to hold is not that it is far away or complicated or hidden. It is hard to hold because thinking itself is a something. Imagining is a something. The very act of considering the question takes place inside a mind, inside a moment, inside the quiet machinery of a brain that exists in space and unfolds in time. You cannot get outside of that to take a look, because there is no outside and there is no looking in a true nothing. The exercise is not merely difficult. It is, in a precise and almost dizzying way, self-defeating. The question contains a trap, and the trap is you. This is not a new struggle. Human beings have been failing at this particular exercise for as long as we have been asking questions at all. Think of the oldest creation stories we have, the ones passed down for thousands of years. The biblical account opens by telling us that in the beginning the heaven and the earth were created. It is a beginning. But notice what it does not say. It does not describe the moment before that beginning. It does not tell you what existed in the place before there was a place, or in the time before there was time. On that question, the oldest text simply goes quiet, not because the people who wrote it were careless, but because the question itself has no foothold. There is nothing there to describe, and language, like imagination, needs a something to hold on to. And it is not only one tradition that falls silent here. Look across the creation stories of the world, and you find the same quiet at the same place. Many of them do not begin with nothing at all. They begin with something already present, a dark water, a formless deep, a cosmic egg, a sleeping giant, a churning sea of chaos waiting to be ordered. The storytellers, in other words, did almost exactly what your mind did a moment ago when it reached for darkness. They could not start from a true nothing either, so they started from the emptiest something they could picture, and they built the world out of that. This is not a failure of those stories, it is a clue. It is thousands of years of human beings, in every culture, arriving at the same wall, and, very sensibly, choosing to begin their tale just on the near side of it. The wall was always there. We have simply always known, somewhere, not to walk straight into it, so you are in good company tonight. The discomfort you feel trying to picture the true nothing is not a private failing. It is one of the oldest shared experiences our species has. And the remarkable thing, the thing that makes this particular night different from all those thousands of years, is that we are now going to walk straight up to that wall on purpose with the tools of modern physics in hand and see exactly how far they let us go. And here is the strange and wonderful turn. Our most careful, most tested, most rigorously checked scientific understanding of the universe runs into exactly the same wall. We will spend the next 2 hours walking toward that wall together, slowly, patiently, building up the physics one careful step at a time. We are going to find that the universe did, in fact, have a beginning. We are going to find that the question of what came before is a real question, not an empty one. And we are going to find an answer that is genuinely unsettling, an answer that suggests the universe may have come from nothing at all. But to understand that answer, to even understand what the words mean, we first have to take apart the word nothing itself. Because by the time we are done, you are going to discover that nothing, the real physical nothing, is far stranger than the blank you just tried and failed to picture. The word nothing, it will turn out, is doing a great deal of quiet work, and most of the confusion that surrounds the question of cosmic origins comes from not noticing how many different things that single small word is being asked to mean. There is the nothing of an empty fridge, which is really a fridge with air in it. There is the nothing of a vacuum, which is really space with the matter removed. And then there is the true nothing, the one with no space and no time and no laws, and that one, we will find, is in a category entirely of its own. Keep all three in mind as we go. Watching which nothing a sentence is actually talking about will be the single most useful skill you can carry through the next 2 hours. Hold on to that failed attempt to picture the blank. We will come back to it right at the very end, and you will find that the failure has changed its meaning by then. For now, just sit with the discomfort of a question that is so easy to ask and so impossible to hold. That discomfort is the doorway. Let us walk through it, slowly, together. Part 2. A universe with a birthday. For most of human history, the universe was assumed to be eternal. It seemed the safest possible assumption. The stars had been there before your grandparents, before their grandparents, before the pyramids, before there were any people at all to look up. Why would it have ever been otherwise? An eternal universe is a comfortable one. It needs no origin story. It simply always was. And so the awkward question of what came before never has to be asked. That comfortable picture is now gone. It did not survive the 20th century. What replaced it is a universe with a birthday. The evidence arrived from several directions at once, and it pointed, stubbornly, at the same conclusion. When astronomers looked carefully at distant galaxies, they found that those galaxies are moving away from us and from each other. The whole universe is expanding, growing larger, the space between things stretching as time goes forward. And if you are willing to take that expansion seriously, you can run the film backward in your mind. If everything is flying apart now, then everything was closer together yesterday, and closer still the day before that. Wind the film back far enough, and you reach a moment when everything was pressed together into an unimaginably hot, unimaginably dense state. Run it back further, and that moment becomes a beginning. It is worth pausing on how strange and unwelcome that conclusion was when it first arrived. The expanding universe was not a result that anyone went looking for. It was not a discovery that physicists wanted. It was forced on them, reluctantly, by the sky itself. Even Einstein, when his own equations first hinted that the universe could not sit still, that it must either expand or contract, recoiled from the idea and added an extra term to his mathematics, specifically to hold the universe steady, to keep it eternal and unchanging the way everyone assumed it had to be. He later regarded that adjustment as one of the great mistakes of his career. The universe, it turned out, did not need to be held still. The universe was moving on its own, and the more carefully astronomers measured, the clearer it became. The galaxies are receding. The space between them is growing. The film, run backward, really does converge. And there was a second clue, quieter than the first, but in some ways even more convincing. If the universe really had once been packed into a hot, dense state, then that primordial furnace should have left an afterglow, a faint warmth still soaking the whole of space, the cooled-down embers of the original fire. And when astronomers learned how to look for it, they found exactly that. A gentle hiss of microwave radiation coming from every direction in the sky at once, the same everywhere. It is the heat of the early universe, stretched and cooled by billions of years of expansion, still arriving. The cosmos had, in effect, kept the receipt. The fire had a beginning, and the beginning left a mark, and the mark is still glowing faintly all around us. Our best measurements now place that beginning at roughly 14 billion years ago. The careful figure that modern cosmology arrives at is closer to 13.8 billion years, but the round number is easier to hold, and the precise decimal is not what matters here. What matters is the shape of the claim. The universe is not eternal. It is not infinitely old. It had a fiery birth, a maelstrom of particles and raw energy, and from that birth it has been expanding and cooling every moment since. The early universe was a furnace. The universe you live in now is cold and sparse and quiet, and it got that way by growing for 14 billion years. Now, sit with what that does to our question. If the universe is eternal, the question of what came before is meaningless, because there is no before. There was never a first moment to stand in front of. But a universe with a birthday is different. A universe with a birthday has a first moment, and a first moment has an edge, and an edge invites you to ask, what is on the other side of it? The moment we discovered the universe was not eternal, we created, almost as a side effect, one of the deepest questions a mind can hold. What came before the beginning? And here is something subtle that is worth slowing down for, because it will become important later. There is a quiet assumption hiding inside the way I just asked that question. When I say what came before the beginning, I am picturing time as a kind of road, a road that stretches back, and the beginning as a point somewhere along it, with more road on the far side. But that picture may be wrong. Time itself, as we will see, may be part of what began. And if time began, then the word before, the word the entire question rests on, may have no meaning at the beginning, the way the word colder has no meaning once you have reached the coldest possible temperature. There may simply be no road on the far side. There may not be a far side at all. We are not ready to settle that yet. But hold it lightly as we go. The question, what came before, is so natural, so irresistible, that it is easy to forget it might be quietly malformed, the way the question, what is north of the North Pole, is malformed. We will return to that pole and that exact phrase much later. Cosmologists, faced with this question, have not been silent. They have offered possibilities, and we will examine several of them carefully before we are through. Perhaps our universe was begotten from some previous existence, one link in an endless chain, a cycle of universes each giving birth to the next. Perhaps our universe was formed in the violent collision between two other universes, struck into being like a spark struck from flint. These are real proposals, made by serious people, and they each have a kind of dignity to them. But there is another answer, and it is the one that this entire video circles toward. It is, by a wide margin, the most unsettling of the possibilities. The proposal is that our universe was born from nothing, not from a previous universe, not from a collision, from nothing at all. And the instant you say that out loud, you feel the problem. It sounds less like physics and more like a contradiction. How does one get something from nothing? How does a universe full of galaxies and stars and stone and breath come out of an absence? It seems to violate the most basic accounting rule we know, the rule that you cannot get out what was never put in. To even begin to answer that, we cannot start with the universe. The universe is too big, and the question of its origin is too vast to attack head-on. We have to come at it sideways. We have to start somewhere much smaller, much stranger, and far closer to home. We have to start with the question of what reality is actually made of, down at its smallest scale, in the world of atoms and the particles inside them. That may sound like a detour. It is not. It is the only road there is. Because the answer to the largest question, where the universe came from, turns out to be hidden inside the answer to one of the smallest, what an electron does when no one is looking at it. The path from the smallest thing to the largest thing is a single continuous path, and we are going to walk every step of it. Around 100 years ago, our answer to the question of what reality is made of fell completely apart, and what grew up in its place is the strangest and the most successful idea in the entire history of science. That is where we are going next. Part 3. When the clockwork stopped. For about 200 years, physics had a picture of the world that worked beautifully, and the picture was a machine, a great clockwork. This was the universe of Isaac Newton, and it was a triumph. In Newton's world, every object had a definite position and a definite speed at every instant. Every object followed exact laws. If a ball rolled across a table, you could, in principle, predict precisely where it would be 1 second later, 1 hour later, 1 century later. The future was not a mystery. The future was a calculation. The universe ticked forward like the gears of a perfect clock. each moment determined entirely by the one before it. That picture matched the world we see. It is, in fact, still the picture your intuition runs on right now as you listen. In the ordinary world, things are things. A cup of coffee set down on a table stays on the table. It does not wander off. It does not blur. It does not become uncertain about where it is. You can set it down and walk away and come back and find it exactly where you left it every single time. Nothing is nothing, and something is something, and objects have definite places, and the world behaves itself. The clockwork holds. I want you to hold on to that cup of coffee, because we are going to come back to it more than once before the night is over, and each time we return to it, it will mean something slightly different. Right now, in this part of the story, the cup is the very emblem of common sense. It is the thing that proves the world is solid and dependable and certain. It is the proof that the strange physics we are about to meet cannot possibly be the whole truth, because look, the cup just sits there, calm and definite, exactly where it should be. The cup is your intuition's best witness. Remember that, by the end, the same cup, sitting in the same calm way on the same table, is going to be telling you the opposite thing, but not yet. For now, let it stand for the dependable world, the world that does not blur, and the depth of the trust we placed in that dependable world is hard to overstate. The clockwork picture was not just a scientific theory, it was, for 2 centuries, a worldview. It promised that the universe was, in principle, completely knowable. It promised that there were no genuine surprises hiding in the foundations, only details we had not yet measured. It promised a cosmos that was, at bottom, reasonable. If you were patient enough and careful enough, the clockwork said, the universe would yield every one of its secrets, because the universe was, in the end, a machine, and machines can be understood. That promise was so deep, so woven into how educated people thought, that when it broke, it did not break quietly. But in the early years of the 20th century, the clockwork stopped. It came apart from 2 directions. From the first direction came Albert Einstein, who took space and time, the 2 things everyone had always assumed were the fixed and rigid backdrop of reality, and showed that they were neither fixed nor rigid. With his theory of relativity, Einstein showed that time can run faster or slower depending on how you move and where you are. He showed that space itself can bend. The stage, it turned out, was not a stage at all. The stage was part of the play. That alone would have been enough to unsettle a century. But from the second direction came something stranger still. Experiments probing the world of the very small, the world of atoms and the particles inside them, began returning results that made no sense. They did not just contradict the details of Newton's clockwork, they contradicted its entire spirit. They suggested that down at the smallest scale, the scale of atoms and electrons, the universe was not running on certainties at all. In that tiny world, physicists found you could not say where a particle was. You could only say where it was likely to be. You could not say how fast it was moving. You could only give the odds. You could not predict what a particle would do next. You could only describe the probabilities of the various things it might do. The clockwork, down at the bottom, was not a clockwork. It was something closer to a game of chance, played by rules nobody had ever seen before. This was not a small adjustment. This was a different kind of universe. For 2 centuries, physics had told us that the world was, at its foundation, certain, and that uncertainty was just a measure of our ignorance. If you did not know where the ball would land, that was a fact about you, about the limits of your knowledge. It was not a fact about the ball. The ball always knew where it was going. The new physics said something almost unbelievable. It said the uncertainty was not in us. The uncertainty was in the world. The particle itself does not have a definite next move. The vagueness is not a gap in our information. The vagueness is real, and it is built into the foundation of everything. It is hard, even now, 100 years later, to feel the full force of how upsetting that claim was. We have grown used to the word quantum. It appears on advertising and in films, and it has lost some of its power to shock. But try, for a moment, to hear it freshly. Physics, the most precise and successful description of the world humans had ever built, the discipline that had predicted the return of comets and the orbits of planets to staggering accuracy, was now saying that at the bottom of reality there is an irreducible haze. Not a haze we could clear away with a better instrument. Not a haze that would lift once we were clever enough. A permanent haze. A built-in fuzziness that no amount of progress would ever sharpen. For people who had been raised to believe that the universe was, in principle, perfectly knowable, this felt less like a discovery and more like a loss. Some of the greatest physicists of the age, Einstein among them, never fully made peace with it. Einstein famously could not accept that the universe, at its foundation, played dice. He spent decades looking for a way around it. He never found one. The dice, as far as anyone has been able to tell, are real. This new physics needed a new mathematics, a new set of rules, and it would come to be called quantum mechanics. And here is the consequence that should already be tugging at you. Every solid, dependable, well-behaved thing in your ordinary world, the cup that stays on the table, the floor that holds you up, your own steady body, all of it is built at the bottom out of these uncertain, probabilistic, rule-bending particles. The certainty you live inside is assembled entirely out of uncertainty. The clockwork you trust is made of dice. There is a natural question that rises up here, and it is a fair one. If the bottom of reality is so uncertain, so probabilistic, so strange, then why is the everyday world so calm? Why does the cup stay on the table? Why does the floor hold? The answer, in brief, is numbers. The strangeness of a single particle gets averaged away when you gather an unthinkable number of them together. A cup of coffee contains so many particles, so many atoms, that their individual quantum hazes blur into a smooth and dependable whole, the way the wild unpredictability of a single coin flip becomes a calm and reliable statistic once you flip the coin 1 trillion times. The clockwork of the everyday world is not a lie. It is real, but it is not the foundation. It is the smooth surface that appears when an ocean of underlying uncertainty is averaged together. The certainty is the appearance. The uncertainty is the truth underneath it. How a person first looked clearly into that strange world, and what they saw there, is one of the great stories in the history of human thought. And it begins, of all places, with a man trying to escape his own runny nose. Part 4. The Island and the Sunrise. In the summer of 1925, a young German physicist named Werner Heisenberg was miserable. He was 23 years old, he was brilliant, and he had a terrible case of hay fever. For months, Heisenberg had been wrestling with the deepest problem in physics. He was trying to understand the atom. Everyone knew, by then, that an atom was built from a small, dense nucleus with electrons somehow arranged around it. The trouble was the somehow. If the electrons simply orbited the nucleus the way the planets orbit the sun, then the laws of physics said the atom should collapse almost instantly. An orbiting electron should bleed away its energy and spiral inward, and the whole atom should wink out of existence in a tiny fraction of a second. But atoms do not do that. Atoms are stable. They last. They build everything. So whatever rule the electrons were following, it was not the rule for planets, and nobody knew what it was. Heisenberg had been attacking this problem for months, and his mathematics kept failing him. Every approach he tried became more tangled, more unwieldy, more unruly, until the equations sprawled across the page and refused to resolve into anything sensible. And then, on top of the intellectual frustration, summer arrived, and with it the pollen, and Heisenberg's hay fever struck hard. His head grew cloudy, his nose would not stop running. His face was so swollen that, at one point, his landlady reportedly thought he had been in a fight, so he ran away. He asked his professor for 2 weeks of leave, and he travelled to a place where there was almost no pollen at all, a tiny, treeless, rocky island called Heligoland, sitting alone in the North Sea. There is something fitting about the setting, and worth noticing. Heligoland is barely an island at all, just a wedge of red rock and a scrap of land beside it, far from any mainland, scoured by wind and sea. It is about as close to nothing as a place on earth gets, and it was on that near-empty rock, surrounded by the simplest possible surroundings, that one of the most intricate ideas in the history of thought was going to come together. He hoped the cold, clean, salty air would clear his head. And it did. As the hay fever loosened its grip, his mind began to clear, and on that small, isolated island, with nothing to distract him, he returned to the problem of the atom. And on Heligoland, he had the idea that changed everything. The idea was almost philosophical, almost humble, and that was its power. Heisenberg realized that he had been trying to do something that could not be done. He had been trying to calculate the precise path of an electron as it orbited inside an atom, the exact route it travelled. But, he asked himself, has anyone ever actually seen that path? Has anyone ever observed an electron moving along its orbit? And the answer was no, nobody ever had. What experiments actually showed you was something different. They showed you the light an atom gave off, the specific colours it emitted as electrons jumped from one state to another. The orbit itself, the path, was never seen. It was an assumption. It was a picture borrowed from planets and quietly imported into a place it did not belong. So Heisenberg made a radical decision. He decided to stop calculating the things he could not observe. He would build his physics only out of quantities that experiments could actually measure, the colours of light, the energies, the things that genuinely show up in the laboratory, the unseen orbit, the comforting picture of a little electron on a little track, he simply set aside. And when he did that, when he stripped his physics down to only the observable, the mathematics that had fought him for months suddenly, finally, worked. The equations came together. The strange new structure clicked into place. The form of those equations looked bizarre to him at first, almost alien, though a mathematician would have recognized them as something called matrices, a tool that is common today, but was a genuine novelty in physics in 1925. Heisenberg did not sleep that night. He was too charged with what he had found. In the small dark hours, he left his lodging and walked out across the rock, and he climbed a tall outcrop at the southern tip of the island, and he sat there, alone, and he waited. And as the sky began to pale, he watched the first rays of the sun lift over the edge of the North Sea. So let us go and sit beside him, because this is a moment worth being inside of, not just told about. It is the middle of the night, then the slow end of it. The island is small and treeless and surrounded on every side by dark water, and there is almost no sound except the sea, the steady working of the sea against the rock, a sound that has not changed in 10,000 years. Heisenberg climbs. The rock is cold under his hands, and cold beneath him when he finally sits. The salt air moves against his face, and his head, for the first time in weeks, is completely clear. The hay fever is gone. The fog of it is gone. There is nothing between him and the thing he has just done. And he has done something enormous, and he knows it, and the knowing will not let him rest. A few hours ago, alone with paper, the equations finally closed. The numbers finally agreed. For months the mathematics had fought him and tangled and refused, and tonight, because he stopped asking where the electron was and asked instead only what he could truly see, it gave way. He is 23 years old, sitting on a rock in the North Sea before dawn, and he is, at this moment, the only person alive who has glimpsed the thing he has glimpsed. The sky goes from black to a deep grey, then to a thin grey, then to something almost like silver. And then the first true light comes over the edge of the water, low and gold and cold, and lays itself across the sea, and reaches him on his rock. And here is the part that no sunrise could ever quite settle. He is not only thrilled, he is also unnerved. Because the layer of reality he has just uncovered, the layer underneath the ordinary world, the layer that quietly builds everything, is not solid, it is not certain. It is not the dependable clockwork he was raised to expect. It is something far stranger, and he has only just begun to see how strange. He watches the sun climb. He has found a new language for the world of the very small, and the world it describes is one he is not sure anyone is ready for. But here is the part that no sunrise could have softened. The world he had found down there was deeply, fundamentally, almost frighteningly strange. He had a working description of the atom at last. But the description did not talk about where an electron is. It talked only about where it might be. It did not give a definite answer for an electron's speed. It gave a vague one. It did not say when an electron would jump from one state to another, only the chance that it would. He had pulled back the curtain on the foundation of reality, and the foundation was not solid. The foundation was made of probability. Heisenberg had found the door. In the next 2 years, he would walk through it and discover, written into the structure of his own equations, a law so deep and so strange that it does not only govern atoms, it governs nothing itself. It governs the empty space between the stars. And it is the first real crack in everything you thought you knew about what nothing is. Part 5. The discovery that nothing is something. 2 years after the sunrise on Heligoland, Heisenberg was staring at his equations again, and he noticed something inside them that he had not put there on purpose. It had simply emerged, the way a hidden shape emerges from a pattern once you finally see it. And what he saw is now called the uncertainty principle, and it is one of the deepest laws of the universe. Here is what he saw. The vagueness in an electron's position and the vagueness in its speed were not two separate facts. They were linked. They were tied together, locked in a trade. The more precisely you pin down where a particle is, the more hopelessly blurred its speed becomes. And the more precisely you pin down how fast it is going, the more its position smears out into a fog. You cannot have both sharp at once. Nature does not permit it. Push one into focus and the other slides away. It is not a limitation of your microscope or your patience. It is a rule built into reality at the deepest level. Let me make that concrete, because it is easy to let it stay abstract, and it should not stay abstract. Imagine you take a single electron and you trap it in a tiny box. In the old clockwork world, this is a simple situation. The electron rattles around inside, bouncing off the walls, and if you want to calm it down, you cool it. Cooling something means slowing its particles. So you cool the electron, and it moves slower and slower, and if you cool it all the way down to the lowest possible temperature, the temperature called absolute zero, the electron should finally come to rest. It should sit still in the middle of its box, perfectly motionless. That is what the old physics says. The uncertainty principle says that is impossible. Strictly, absolutely impossible. And the reason is beautiful. By putting the electron in a small box, you have done something. You have pinned down its position. You know where it is, because it has to be somewhere inside those walls, and the box is small. But the uncertainty principle says that the instant you know the position that well, the speed must become uncertain. There must be a fuzzy spread of possible speeds. And a fuzzy spread of possible speeds means the electron cannot simply be sitting still. Because sitting still is one exact speed, the speed of 0, and an exact speed is forbidden when the position is known. So the electron cannot stop. No matter how cold you make it, no matter how close you crawl toward absolute 0, the electron keeps a residual jiggle, a leftover restlessness that can never be cooled away. The universe will not let it be still. Now hold that result, because here comes the step that breaks the floor open. Heisenberg's trade-off does not only apply to position and speed. There is a second pairing, just as deep, and it is the pairing of energy and time. Energy and time are locked in the very same kind of bargain. And what that means is this. Over a very short stretch of time, the energy of a region is not a fixed, settled, definite quantity. It is uncertain. It can fluctuate. Small amounts of energy can flicker into existence and flicker back out, appearing and vanishing on timescales so brief that the universe, in effect, never catches them. For those vanishingly short moments, energy is not conserved. The oldest accounting rule in physics, the rule that energy can be neither created nor destroyed, turns out to have a loophole, and the loophole is written into the structure of time itself. And now, follow this to where it leads. Take a region of space and empty it. Take out every atom, every particle, every ray of light and heat. Make it as empty as the laws of physics allow. You would call that nothing. Everyone would. But the uncertainty principle says that even this perfect emptiness cannot have a fixed, definite, settled energy. Its energy must fluctuate. And so, in that supposedly empty space, energy is constantly flickering into being and flickering away. Pairs of particles, called virtual particles, are constantly appearing out of the emptiness and vanishing back into it, borrowing their brief existence from the uncertainty in energy and paying it back before the universe can object. This restless, jittering, ever-present activity has a name. It is called the quantum vacuum, and it does not sit in one special laboratory. It fills the entire universe. It is in the space between the stars. It is in the space between the walls of your room. It is in the gap between your hand and this surface, right now. Let us go there. Let us slow everything down and go into a patch of that empty space and look. Choose somewhere genuinely, perfectly empty, out between the stars, far from any planet, far from any sun, a region of the cosmos where there is no matter at all, no dust, no light passing through, nothing. By every ordinary measure, the emptiest place there is. Stand in it, in your mind, and let your perception slow down, slower, slower, until you can perceive events that last for almost no time at all. And now watch. The emptiness is not still. Everywhere, in every direction, faint and constant, there is a flicker. Pairs of particles are appearing out of nothing, two at a time, holding their brief existence, and then meeting again and vanishing back into the nothing they came from. It is happening here, and here, and here, all through the space around you, ceaselessly. Each individual flicker is unimaginably brief, a borrowing of existence so short that the universe never has time to object, the energy returned before the debt can be called. But there are countless such flickers, everywhere, always. The emptiness shimmers with them. It is less like a still dark room, and more like the surface of water seen very close up, never smooth, always trembling, alive with a fine restless motion that never stops and never started, because it has simply always been doing this. This is what the uncertainty principle guarantees is there, not as a theory, as a fact about the emptiest place you could ever go. The void is not a void. It is quietly, endlessly busy, and it has been busy in exactly this way, in every cubic inch of empty space, everywhere, for the entire history of the universe. And so we arrive at the conclusion that will carry us all the way to the end of this video, and I want to state it as plainly as it can be stated. In the quantum world, empty space is not empty. the most perfect nothing that physics allows, is still humming with activity, still alive with particles coming and going, still buzzing with borrowed energy. Nothing is not nothing. Nothing, it turns out, is something. Sit with that, because you have lived your whole life inside a quiet assumption that emptiness is simply absence, and the physics has just told you that this assumption is false. There is no perfect blank. There never has been. The void itself jitters. And I want you to feel where that lands, because it lands closer to you than it might first seem. It is tempting to file this away as an exotic fact about deep space, something true far away and irrelevant here. But it is not far away. The quantum vacuum is not somewhere else. It is here. The empty space in the room around you, the air notwithstanding, the space itself, is humming with this activity. The small gap between your hand and whatever surface is nearest to it is humming with it. The space inside your own body, the space between the atoms that make you up, and there is a great deal of that space, is humming with it. You have spent your entire life immersed in this restless vacuum, and so has everyone who has ever lived, and so has every star and every world. You have never, not for one single instant, been surrounded by genuine, perfect, empty nothing. It was never available. The emptiest moment of your life was still full. This is the first emotional turn of our journey, and it is worth marking it. The word nothing has just quietly changed its meaning under your feet. And if even empty space is secretly full of activity, then the question we started with, the question of whether a universe could come from nothing, has changed its shape entirely. Because we are going to have to ask very carefully, every time the word appears, which nothing we are actually talking about, we will get there. But first, we need to see that this jittering vacuum, this restless nothing, is not some delicate curiosity confined to the small. It reaches up. It reaches all the way up to the stars. And without it, the sun above you would not shine. Part 6. The loophole that lights the stars. For a long time, one of the most embarrassing problems in all of science was the sun, not the existence of the sun, the age of it. In the 1800s, the great physicist, Lord Kelvin, the man who worked out the very idea of absolute zero, the man whose name we now use for the units of temperature, turned his mind to the question of how the sun could burn. He understood the sun as an enormous ball of gas, squeezed to ferocious temperatures by the crush of its own gravity, and he calculated how long such a ball could keep shining. His answer was troubling. He decided the sun had probably not been lighting the earth for more than 100 million years, and almost certainly not for 500 million. That sounds like a long time. It is not long enough. Geologists, studying the slow weathering of mountains and the patient laying down of rock, needed far more time than that. Biologists, studying the slow unfolding of life, needed far more still. Lord Kelvin's sun ran out of fuel long before the Earth's own story could possibly have happened. Something was badly wrong, and to his credit, Kelvin himself left a door open. He wrote that his limit would have to be revised if some source of energy, in his words, now unknown to us, were prepared in the great storehouse of creation. He was right. There was a source unknown to him, and it was hiding inside the atom. By the early 20th century, physicists had worked out the structure of the atom. A tiny, dense nucleus at the center, packed with positively charged protons and uncharged neutrons, and the electrons arranged around it. And they had recognized that holding that nucleus together required a tremendous force, because the protons inside it are all positively charged, and like charges push each other apart, fiercely, especially when crammed as close as they are inside a nucleus. The force that overpowers that repulsion and binds the nucleus together is, with admirable bluntness, called the strong force. And the strong force, the physicists realized, holds an enormous reservoir of energy. If you could find a way to tap it, energy would pour out. In 1920, the astronomer Arthur Eddington put the pieces together and proposed the answer. The sun, he said, shines by tapping the energy inside atomic nuclei. Stars are powered by nuclear fusion, the process of forcing light atomic nuclei to join together into heavier ones. The sun is mostly hydrogen, the simplest element there is, and when hydrogen nuclei are fused together, a flicker of their mass is released as energy. Do that on the colossal scale of a star, and you get sunlight. You get a furnace that can burn not for a few 100 million years, but for billions. It was the right answer. And notice, before we go on, that it is a kind of answer to a smaller version of our larger question. Lord Kelvin had, in effect, run into a wall. By the physics he knew, the sun could not last long enough, and the wall seemed perfectly solid. The resolution did not come from measuring the sun more carefully. It came from discovering that there was a hidden reservoir, a source of energy, in Kelvin's own words, then unknown, sitting quietly inside the atom. The wall was not a true wall. It was the edge of what that generation of physics could see. That pattern, a wall that turns out to be only the edge of a theory rather than the edge of reality, is going to come back. When we reach the great locked door at the end of this video, you should ask yourself which kind of wall it is. But the right answer came with a problem of its own, and the problem was severe. To fuse two hydrogen nuclei, you have to bring them close enough to touch, close enough for the strong force to grab them, because the strong force only works across an almost absurdly tiny distance. The two nuclei essentially have to make contact, but both of those nuclei are protons, and protons are positively charged, and as you push them toward each other, they push back, harder and harder, with that fierce electric repulsion. To overcome the repulsion and get them to touch, you need to throw them together with tremendous violence. You need tremendous heat, and here was the disaster. Astronomers calculated the temperature at the core of the sun, the temperature produced by the sun's own gravity bearing down on its center. The number they got was about 15 million degrees. 15 million degrees is staggeringly hot, and it is not nearly hot enough. At 15 million degrees, the hydrogen nuclei in the sun's core are moving fast, but not fast enough. When two of them rush at each other, the electric repulsion stops them and turns them back long before they ever get close enough to touch, long before the strong force can take hold. The collisions are too gentle. The barrier is too high. By the straightforward physics of the time, the sun simply could not work. It was not hot enough to burn, and yet it was burning. The sky was bright. Something had to be giving. The thing that was giving was the same strange physics we have been building all along. The answer came from a physicist named George Gamow, born in the city of Odessa, a true polymath whose curiosity ranged across the whole of science. And Gamow understood something the older calculation had missed. He understood that you cannot treat two colliding nuclei as if they were solid little balls of matter, two marbles clacking together. Because of the uncertainty principle, a nucleus does not have one single definite position. It is fuzzy. It is, in a real sense, smeared across a range of possible locations all at once. And that smearing changes everything. When two nuclei rush toward each other and the electric repulsion turns them back, they do not, as solid balls would, simply stop at a clean, fixed distance. They are fuzzy, they are spread out, and somewhere in that fuzzy spread of possible positions, there is a small but real chance that the two nuclei find themselves close enough to touch, close enough for the strong force to seize them, even though, by the old reckoning, they never had the energy to get there. It is as if the nuclei passed straight through a wall they could never climb. Physicists call it quantum tunneling. The barrier of electric repulsion is a wall, and the nuclei do not go over it, they go through it. Not always, not even often. In fact, for any single pair of nuclei, tunneling through the barrier is wildly unlikely, a rare event, a long shot. But here is where the numbers come in again. The core of the Sun is not a calm place with a few nuclei in it. It is a furnace packed with an almost incomprehensible quantity of hydrogen, and in it, nuclei are colliding at a rate beyond any counting, collision after collision after collision, every fraction of every second, for billions of years. And when you have that many attempts, even a long shot pays out steadily. A rare event, given enough chances, becomes a reliable trickle. That trickle of successful tunnelings is enough. It is enough to keep the fusion burning. It is enough to keep the Sun alight, steadily, for billions of years, so let this land properly. The Sun does not shine because it is hot enough to. By the rules of the ordinary world, the world of solid objects in certain positions, the Sun is too cold to burn, and the sky should be dark. The Sun shines because of a loophole. It shines because the particles in its heart are not solid certain things, but fuzzy, uncertain, probabilistic things, and that fuzziness lets them slip through a barrier they could never otherwise cross. The same strangeness Heisenberg found on his island, the same uncertainty that fills empty space with its restless humming, reaches all the way up into the heart of a star and lets it burn. And I want you to feel the change in scale that has just happened, because it is the heart of this part of the journey. When we first met the uncertainty principle, it was a rule about electrons, tiny things, things so small they seemed to belong to a separate, sealed-off world, a world that had nothing to do with the large, warm, ordinary one. It was easy to think, fine, the very small is strange, but the strangeness stays down there. It does not climb out. The cup stays on the table. But it does climb out. The very same rule, the very same fuzziness, is the reason a star 1,000,000 times the size of the Earth manages to shine. The quantum world is not sealed off. It is not a separate basement of reality that we can safely ignore. It is the foundation, and the foundation holds up the whole house. The strangeness is not down there. The strangeness is everywhere, and it is doing load-bearing work. The line between the quantum world and the ordinary world, the line you have probably always quietly assumed exists, is not real. There is only one world, and it runs, top to bottom, on these rules. The warmth on your skin on a clear day is quantum mechanics. The light that lets you see is quantum mechanics. The strange world of the very small is not far away and irrelevant. It is the reason the day is bright. And, as we are about to see, it is also the reason you exist at all. Part 7. The quantum forces that built you. The Sun shines by fusing hydrogen into helium, and for a star like our Sun, that is most of the story. But the universe needed more than hydrogen and helium. It needed carbon, the backbone of every living thing. It needed oxygen, to breathe. It needed nitrogen and phosphorus and calcium and iron. None of those elements existed in any quantity when the universe was young. They had to be built. And the place they were built was inside stars. Through the 1940s and 50s, in an effort sharpened by all the nuclear research of the Second World War, astronomers slowly uncovered the secret inner lives of stars. They worked out the long chain of nuclear fusion that runs inside them. Hydrogen fuses into helium. Then, in hotter and older stars, helium fuses into carbon and oxygen. And in the most massive stars of all, the fusion climbs further still, building heavier and heavier elements, all the way up to iron. But this element building is fussy work. It demands the most extreme conditions in the universe. The crushing temperatures and densities found only in the cores of giant stars, where the sheer weight of the star bearing down creates a furnace fierce enough to forge the heavy elements. And so the stars become factories. Deep in their cores, across millions of years, they manufacture the raw material of planets, of oceans, of bones, of blood. But there is a catch, and it is a serious one. The elements are made in the core, locked away in the very center of the star, buried under its entire crushing weight. Carbon and oxygen and iron forged in a stellar core are, for the moment, useless. They are treasure sealed inside a vault. For those elements to ever become a planet or a person, the star has to give them up. The vault has to open. And the vault opens in the most violent event the universe has to offer. It opens when a massive star dies, in the catastrophe we call a supernova. And quantum mechanics, the same physics that lit the star in the first place, is also what tears it apart and scatters its treasure across space. To see how, I have to introduce you to the strangest particle in physics. It is called the neutrino. The neutrino has almost no mass at all. It has no electric charge. Because it has no charge, electric and magnetic fields are completely invisible to it. It does not feel the strong force that binds nuclei. The neutrino, in fact, ignores almost every force there is. It responds to only one of the fundamental forces, the faintest and strangest of them, a force called the weak force, first proposed by the physicist Wolfgang Pauli in the 1930s. Because the neutrino interacts so feebly with everything, it is almost impossible to catch. Let me give you a sense of just how slippery it is. A neutrino could fly straight through a solid block of lead, an entire light-year thick, and most likely sail clean out the other side without ever once touching an atom. A light-year of solid lead, and the neutrino treats it like an open window. That is how reluctant this particle is to interact with anything. It is so elusive that, after Pauli first proposed it, it took physicists about 25 years to finally, painstakingly, catch one in an experiment. And yet this ghostly, barely there particle is the hero of the supernova. Here is what happens. When the core of a massive star finally runs out of fuel and collapses, the matter in that core is crushed together with unbelievable force. Electrons are jammed into protons. And that violent merging produces neutrinos, an almost incomprehensible flood of them, vastly more than you could ever count. Now, neutrinos normally ignore matter. We just said so. A neutrino treats a light year of lead like a window. But the collapsing core of a dying star is no ordinary matter. It is the densest stuff in the universe outside of a black hole. And the flood of neutrinos pouring out is so torrential that, even though each individual neutrino almost certainly does nothing, the sheer number of them means that enough of them do slam into the infalling layers of the star. And by their sheer overwhelming numbers, those barely interacting ghost particles deliver a blow strong enough to halt the collapse, reverse it, and blast the outer layers of the star into space. That is the supernova. And riding outward on that blast are all the elements the star spent its life forging, the carbon, the oxygen, the iron, flung across the galaxy, mixed into great clouds of gas and dust, the raw material for new stars, new planets, and eventually for you. Pause on the strangeness of that mechanism for a moment, because it is genuinely one of the most counterintuitive things in all of physics, and it is easy to let it slide past. The particle that blows the star apart is the particle that interacts with almost nothing. The neutrino is famous, defining, for its reluctance to touch matter. It is the ghost. It is the thing that sails through a light year of lead. And yet, in the dying core of a massive star, it is the neutrino, and only the neutrino, that delivers the killing blow. How? Not by being powerful, by being numerous. Each individual ghost still almost certainly does nothing. But when you release an unthinkable flood of them into matter dense enough that even a ghost's tiny chance of interacting starts to add up, the sheer arithmetic of their numbers turns the most aloof particle in the universe into a sledgehammer. It is a lesson the universe teaches in many places. Enough almost nothings gathered together become a something. Hold that thought, It is closer to the heart of this whole video than it might seem. So I want you to feel the full weight of this, because it is not a metaphor and it is not poetry. It is plain physical fact. The carbon in every cell of your body was assembled inside a star by quantum forces in a fusion process that depends on the uncertainty principle. The oxygen you are breathing in right now was forged the same way. The calcium that stiffens your bones, the iron that rides in your blood and carries oxygen to every part of you, all of it was built in a stellar core and then thrown out into space by a flood of ghost particles obeying the weak force. Let that settle slowly, because it is the second great emotional turn of this journey, and it deserves to be felt and not just noted. Up to now, the strangeness has been something happening out there, in an atom, in the sun, in the deep dark, between the stars. You have been a spectator, listening to a strange story about a strange universe. But the iron in your blood is not out there. It is in your wrist, in the slow pulse you could feel right now if you went looking for it. And that iron was forged in the heart of a star you will never see by quantum tunneling, and then flung across the galaxy by a torrent of ghostly particles obeying the weak force, and it drifted for an unimaginable span of time, and it gathered into a cloud, and the cloud became the sun and the earth and, eventually, you. You are not an observer standing outside of quantum mechanics, watching it from a safe distance. There is no safe distance. There is no outside. You are made of its products. Every atom, heavier than the simplest few, was manufactured by these strange rules and delivered to you by these strange forces. The quantum world is not a place you are looking into. It is the thing you are looking with. The strange physics of the very small did not just light the sky for you. It assembled the body you are listening with, the eyes that would read these words, the brain that is holding this thought. You are, in the most literal and unmetaphorical sense available, what quantum mechanics does when it is given 14 billion years and a great deal of hydrogen. And once you truly absorb that, once you feel that the quantum world is not out there but in here, a much larger question becomes impossible to avoid. If quantum mechanics built the stars and the elements and you, then how far does its reach extend? Could it reach the whole universe? Could the entire cosmos be a quantum object? That is the question we turn to now. Part 8. A single equation for everything. We need to look more carefully at the central tool of quantum mechanics, the thing that does the describing. It is called the wave function. And the wave function is where this story begins to grow truly vast. When Erwin Schrödinger wrote down his famous equation in 1925, the same year Heisenberg was on his island, he gave us a new way to describe a particle. In quantum mechanics, an electron is not a tiny dot at a definite location. It is described by a wave function, a mathematical object that is spread out and fuzzy, and that contains, encoded within it, everything that can be known about that particle, where it might be found, how fast it might be going, every possibility with every probability. The wave function holds it all. So far, that is a description of one particle. But here is the feature that opens the door to everything that follows. In quantum mechanics, you do not have to describe two particles with two separate wave functions. You can describe them both with a single shared wave function. One mathematical object that holds the full quantum state of both particles together, and it does not stop at two. 3 particles, 1,000 particles, 1,000,000,000,000 particles, all of them can be folded into one single wave function. There is, in the mathematics, no limit. And once you notice that, a staggering question opens up in front of you, and it may be the largest question that can be asked. If a single wave function can describe any number of particles, then could you write down a single wave function that describes every particle in the entire universe, every atom, in every star, Every photon of light streaming across every distance. The whole cosmos, all of it, captured in one immense mathematical object. The wave function of the universe. It would be the most complex thing imaginable, but the physics says it is not impossible. It is, at least in principle, allowed. And if such a thing exists, then the entire universe is a single quantum object, and it carries with it all the strangeness that quantum objects carry, including the strangest feature of all, which is what quantum mechanics does to the future. Think back to Newton's clockwork. In the old deterministic universe, the future was fixed. If you somehow knew the exact position and exact speed of every particle at one instant, you could calculate the entire future of the universe, every detail, forever. The future was already written into the present, complete and inevitable, waiting only to be revealed. There was one future, and it was certain. Quantum mechanics shatters that. If you know the wave function of a system today, the equations will indeed tell you the wave function tomorrow. So far, that sounds deterministic. But the wave function tomorrow does not describe one single definite outcome. It describes a whole spread of possible outcomes, each with its own probability. The wave function tells you the odds. It does not tell you the result. There is not one future written into the present. There is a vast branching fan of possible futures, and quantum mechanics, on its own, does not tell you which one becomes real. This is a genuine crisis at the heart of the theory, and physicists have wrestled with it for decades. Which of the possible futures actually happens? What picks the winner? In the 1950s, a physicist named Hugh Everett III offered an answer so bold that most of his colleagues simply could not accept it. Everett's answer was that no future is picked. They all happen. Every possible outcome described by the wave function actually occurs, each one in its own branch of reality. The universe, in this view, is constantly splitting, dividing into countless versions, one for every possible result of every quantum event. It is called the many worlds interpretation, and it means that there are other versions of this universe, fantastically many of them, and other versions of you. In some of those branches, your life took a different turn. In some, a small choice went the other way. In some, the differences are vast, and in some, they are almost nothing at all. I want to be careful here, because this is exactly the kind of idea that gets stretched in ways the physics does not support. The many worlds picture is a serious interpretation of quantum mechanics, taken seriously by serious physicists, but it is also frequently misread. It is sometimes told as though it means that anything you can imagine is happening somewhere, that every story, every wish, every fantasy is real in some branch. That is not what the physics says. The branches follow from genuine quantum outcomes, governed strictly by the wave function. They are not generated by human imagination or human wanting. There is a grain of real physics here, and there is a great deal of fiction piled on top of it, and it is worth keeping the two apart. The honest version is strange enough without the embellishment. The honest version simply says that the wave function may describe many outcomes, and many worlds is the interpretation that takes all of them to be equally real. Everett's idea was too radical for the physics of his time. It was largely dismissed and ignored, and Everett, discouraged, eventually left physics altogether and never returned to it. But the idea did not leave with him. It survived. It is taken seriously today, debated by serious people, one of the genuine live contenders for what the wave function really means. The man was set aside by his field. The thought outlasted him. And here is why all of this matters for our question. If the universe has a wave function, then perhaps that wave function can tell us something about the universe's beginning. Stephen Hawking thought so. Working with the physicist Jim Hartle, Hawking asked whether treating the whole universe as a quantum object could resolve the oldest problem in cosmology, the problem of the beginning itself. And what they proposed was subtle and strange. They argued that in the earliest moments of the universe, time did not behave like time. The quantum nature of those first instants made time indistinct, blurred, not yet fully itself. Time, in their picture, only gradually came into being as the universe grew larger and more definite. And if that is true, then the troubling moment of the beginning, the sharp first instant that seems to demand an explanation, may simply dissolve. There is no clean first moment, because in those earliest conditions there was no sharp time for a first moment to sit inside. The beginning is not a wall you slam into. It is more like a place where the very notion of before quietly stops making sense, the way the idea of north stops making sense once you are standing exactly on the North Pole. The question does not get answered. The question gets gently dismantled. Not everyone accepts that picture, and the debate is very much alive. Some physicists find it elegant. Others find it a sleight of hand, a way of making a problem disappear by quietly assuming what it set out to explain. That disagreement, that unsettledness, is itself worth noticing. We are at the frontier here, the genuine working edge of physics, where careful people look at the same equations and come away with different convictions about what the equations mean. There is no quiet consensus to hand you. There is an open question, and honesty requires saying so. But notice what has happened to our journey, regardless of which interpretation turns out to be right. We have gone from quantum mechanics describing a single electron, a tiny thing in a laboratory, to quantum mechanics describing the entire universe, and even reshaping what we mean by its beginning. The strangeness has scaled all the way up, from the smallest thing there is to the largest. There is nothing left for it to climb. And in the next part, we are going to see the quantum vacuum, that restless humming nothing from the fifth part of this video, do something with its own hands. Something you can still see in the sky tonight. We are going to watch it build the galaxies. Part 9. The quantum seeds of every galaxy. In the 1970s, a young physicist named Alan Guth was thinking about the very early universe, and he was thinking in particular about something he needed to get rid of. He had a problem to hide. The problem was magnetic monopoles. Let me explain what a magnetic monopole is and why it was such a nuisance. Take any magnet you have ever held, a bar magnet, a fridge magnet, anything. It has two ends, a north pole and a south pole. And here is a curious fact you may never have stopped to notice. You cannot separate them. Cut a bar magnet in half, hoping to get a north piece and a south piece, and you do not. You get two smaller magnets, each with its own north and its own south. Cut those in half, and the same thing happens. No matter how far you go, you never isolate a single pole. North and south always come together. But many physicists strongly suspected that single poles, magnetic monopoles, an isolated north or an isolated south, ought to exist. The reason came from theories of the very early universe. In the first unimaginably hot moments after the beginning, many physicists believed the four forces of nature we know today were not yet separate. They believed all of them were unified into a single grand superforce, and that only as the universe expanded and cooled did this superforce fracture into the distinct forces we now see. And the mathematics of those unified theories said that, as the superforce fractured, the process should have produced magnetic monopoles, and produced them in great abundance. So the universe should be littered with monopoles, and it is not. We have looked, we do not find them. If the unified force picture was right, where had all the monopoles gone? Guth needed to hide them, and in 1981 he found a way. And the way turned out to be one of the most important ideas in modern cosmology. Guth proposed that very early in its history, when it was a tiny fraction of a second old, the universe underwent a sudden, violent, almost unimaginably rapid burst of expansion. In the briefest sliver of time, a region of the cosmos ballooned outward, growing by an enormous factor. He called it inflation, and inflation solved the monopole problem beautifully. If the universe expanded that explosively, then whatever monopoles existed got spread out, diluted, scattered across a volume so vast that you might be left with only a single monopole in the entire observable universe. Effectively undetectable, the monopoles were not destroyed, they were simply thinned out into invisibility. But when Guth looked harder at his idea, he realized it did much more than tidy away an embarrassing particle. It explained something far deeper, something about the universe that had quietly puzzled cosmologists for years. It explained why the universe is so smooth. When you look at the universe on the largest scales, across millions and billions of light years, it is astonishingly uniform. Look in one direction, then turn and look in the completely opposite direction, and the universe looks essentially the same. The same kind of structure, the same temperature, the same everything, and that is strange when you think about it. Why should two regions of the cosmos, impossibly far apart, having never had any contact, look so identical? Left to pure chance, you would expect lumps and patches, some regions denser, some thinner, a cosmos of uneven texture. Inflation explained the smoothness in a single elegant stroke. Before inflation, the region that would become our entire observable universe was tiny, truly tiny. And a tiny region is naturally uniform, naturally smooth, simply because it is small and all its parts were in close contact and could even themselves out. Then inflation seized that tiny smooth patch and blew it up to cosmic size in an instant. The smoothness of the heavens, that vast uncanny uniformity, is just the smoothness of a microscopic patch stretched across the whole sky. And now we arrive at the heart of this part, the place where the quantum vacuum reaches out and shapes everything you have ever seen in the night sky. That tiny patch of space, just before inflation stretched it, was not perfectly, mathematically smooth. It could not be, because that tiny patch contained the quantum vacuum. And the quantum vacuum, as we learned in Part 5, is never still. The uncertainty principle keeps it forever jittering, with energy and matter flickering in and out of existence everywhere within it. So the patch was very nearly smooth, but it was textured by these minuscule quantum fluctuations, tiny ripples of slightly more energy here, slightly less there, appearing and vanishing. Then inflation happened. And inflation, blowing that patch up to enormous size with incredible speed, did something remarkable to those tiny quantum ripples. It froze them. It stretched them out and locked them into the fabric of space before they could flicker away. The fleeting jitter of the quantum vacuum became a permanent feature of the cosmos, printed onto reality. When inflation ended, the colossal energy that had driven it was dumped back into the universe as a flood of matter and radiation. And because the frozen quantum ripples were still there, that matter was not spread perfectly evenly. There was very slightly more matter in some places, very slightly less in others. The difference was almost nothing, less than 1 part in a billion, a faint unevenness. But it was enough, because gravity is patient, and gravity always pulls. Let us go and watch it happen. Stand, in your mind, in the universe just after inflation has ended. The colossal stretching is over. The space around you is enormous now, and filled with a hot, faintly glowing fog of matter and radiation, almost perfectly even in every direction. Almost. Look closely at one small region, a region that, before inflation seized it, you could have covered with the palm of your hand. Frozen into it is a faint unevenness, a place where there is the smallest possible excess of matter, a part in a billion more than the fog around it. It is nothing. It is almost literally nothing, a difference so slight you would never see it. But now let the time run forward, fast, hundreds of millions of years compressed into the space of a held breath. Watch that faint excess. Gravity has found it. Gravity has a fraction more to grip there, and gravity does not rest and does not relent. The slightly denser patch pulls. Matter from the surrounding fog drifts toward it, slowly at first, then less slowly. The patch grows denser, and a denser patch pulls harder, and so it gathers more and grows denser still. What was a part in a billion whisper becomes a clump, and the clump becomes a vast gathering cloud, and the cloud, at its crowded, heating center, reaches the threshold. And there, in that exact spot marked out long ago by a quantum flicker, the first light of the first star switches on. You have just watched a galaxy being drawn by gravity directly out of a tremble in the quantum vacuum. The slightly denser regions grew denser still. Over hundreds of millions of years, those faint overdensities gathered material, drawing it in, concentrating it, until at last, in those exact spots, the matter became dense enough and hot enough to ignite, and the first stars switched on. So follow the chain, because it is one of the most extraordinary chains in all of science. The galaxies are not scattered randomly. They grew in the places where matter was slightly denser. The places where matter was slightly denser were determined by quantum fluctuations frozen in during inflation. And those quantum fluctuations were the jittering of the quantum vacuum, the restless trembling of nothing. Every galaxy that exists, every star, every world, including this one, grew from a seed. And the seed was a quantum flicker in empty space. And this is not a story we have to take on faith. That faint original unevenness is still visible. It is written across the whole sky in the oldest light in the universe, the cosmic microwave background, the afterglow of the early cosmos. When we map that ancient light, we see the pattern of slightly warmer and slightly cooler patches, the direct fossil imprint of those primordial quantum ripples. We are, quite literally, looking at a photograph of the quantum vacuum taken when the universe was young. You came from one of those ripples. The structure of the entire universe is the fossil of a tiny uncertainty. Let that sit, because it quietly rearranges your place in the story. We tend to think of galaxies as the grand, permanent furniture of reality, the big, solid facts, and of quantum fluctuations as fleeting and trivial, the small print of physics. This gets the relationship exactly backward. The galaxy is the consequence. The quantum flicker is the cause. The grand structure is the echo, stretched and frozen and grown, of something that, on its own, lasted less than an instant and involved less than nothing. Every spiral arm you have ever seen in a photograph, every cluster of stars, every place in the cosmos where matter gathered itself into something rather than spreading out into a featureless haze, traces back to the trembling of the vacuum. The universe did not start smooth and then develop lumps by accident. It started with the faintest possible lumps, written in by quantum uncertainty, and gravity spent billions of years patiently amplifying them into everything. And if quantum nothing can seed a galaxy, then we are finally ready to ask the question this whole video has been walking toward. We have watched the restless vacuum light a star and build a body and grow a galaxy. There is one thing left to ask of it, the largest thing. Could quantum nothing seed a universe? Part 10. The universe as a vacuum fluctuation. The year is 1973. Let us be in the room. It is a lecture hall, the ordinary kind, rows of seats, a speaker at the front. The speaker is Dennis Sciama, one of the most respected cosmologists of the age, a man who taught many of the great names of the field. The room is full of physicists, attentive, following the argument. Among them, partway back, sits a young physicist named Edward Tryon. He is listening. He is not planning to say anything. And then there is a pause in the lecture, one of those small, natural gaps that open up when a speaker draws breath or turns to the board. And into that gap, into that quiet, Edward Tryon hears a voice. It takes him a half-second to register that the voice is his own, that the words have already left him before he chose to release them. He has said, "Maybe the universe is a vacuum fluctuation. There is a ripple of laughter in the room, and you can understand the laughter." Heard cold, in the middle of someone else's lecture, it sounds exactly like a joke, a clever aside, the kind of remark a physicist tosses out to lighten a long afternoon. Siama, gracious, lets it pass, and continues, and the lecture moves on, and the room forgets it within the minute. But Edward Tryon, sitting back down into the small private silence after his own unplanned sentence, was not joking. He had meant it. The idea had risen up out of him, fully formed, before his caution could catch it, and now it was out, and it had been laughed at, and he could not let it go. Sometimes, the most serious idea a person ever has arrives disguised as a joke, and arrives, of all places, in the middle of someone else's talk. Tryon went home with it, and he did not put it down. Later that same year, in December of 1973, Tryon published a scientific paper, and the title of that paper was, almost word for word, the sentence he had blurted in the lecture hall: "Is the universe a vacuum fluctuation?" He was asking the question in earnest now, in print, to the entire physics community, and the reasoning behind it is something we are now, finally, fully equipped to understand. Everything in this video has been preparing you for it. Start with what we learned in Part 5. The quantum vacuum is restless. The uncertainty principle ties energy and time together, and so the energy of empty space is never fixed. It fluctuates. Energy can flicker into existence and flicker away, and the more briefly it borrows its existence, the more energy it is allowed to borrow. Small fluctuations lasting a long time. Large fluctuations lasting only an instant. That is the rule. Now, Tryon asked a daring question. What if the universe itself is one of these fluctuations? What if everything we see, all the matter, all the energy, all the galaxies, is a fluctuation of the vacuum, the same kind of event as a virtual particle flickering into being, only unimaginably larger? The obvious objection leaps up immediately. A vacuum fluctuation is allowed to be large only if it is incredibly brief. And the universe is not brief. The universe has lasted 14 billion years and shows every sign of continuing. The universe is the very opposite of a fleeting flicker. So, how could it possibly be a fluctuation? The numbers seem to forbid it instantly. And here is where Tryon made the move that gives his idea its strange and lasting power. He asked a question almost nobody had thought to ask. What is the total energy of the universe? Add it all up. Every star, every particle, every motion, every photon of light. What is the grand total? Your first instinct is that the total must be staggeringly, almost infinitely huge. Look at all the matter. Look at all the energy. Surely the sum is beyond enormous. But Tryon knew that energy comes in two signs. There is positive energy, and that is what all the matter and all the motion represent, an immense positive quantity, exactly as your instinct says. But there is also negative energy. Gravity, it turns out, contributes negative energy. The gravitational field, binding all the matter of the universe together, carries energy, and the sign of that energy is negative. And there is a tremendous amount of it, because there is a tremendous amount of gravity. So the total energy of the universe is a sum of two competing pieces, a vast positive number from all the matter and motion, and a vast negative number from gravity. And Tryon's electrifying suggestion was this. What if those two numbers, the huge positive and the huge negative, balance? What if they cancel? What if the total energy of the universe, everything added together, comes out to exactly zero? This is a real possibility. It is not a trick. It is genuinely consistent with what we understand, that the books of the universe may balance perfectly, that the immense positive energy of all the matter is exactly offset by the immense negative energy of gravity, leaving a grand total of nothing. And if that is true, the objection that seemed to instantly kill the idea simply vanishes. Remember the rule: a large fluctuation must be brief, but that rule is about energy. A fluctuation that involves a lot of energy cannot last long. But a fluctuation of zero energy is a different thing entirely. A fluctuation that costs nothing, that involves no net energy at all, does not have to be brief. A zero-energy fluctuation can last as long as it likes. A zero-energy fluctuation can, in principle, last forever. And so Edward Tryon arrived at his conclusion, the conclusion he had blurted out before he understood it himself. The entire universe may be a vacuum fluctuation, a flicker of the quantum vacuum, exactly like the virtual particles winking in and out of empty space, except that this particular flicker has a total energy of zero, and so, instead of vanishing in an instant, it persists, it endures, it becomes a cosmos. It becomes stars and worlds and the long patient unfolding of 14 billion years. It becomes us. Sit with that for a long moment, because it is one of the strangest ideas a human mind has ever put down on paper, and it deserves real quiet, the kind of quiet you give to a thought that might actually be true. We have always assumed, deep in our bones, far below the level of argument, that existence is expensive, that to have a universe, you must somehow pay for it. That something this vast, this full, this heavy with stars, must have come from somewhere, must be accounted for, must be balanced against some enormous cost. It is one of the most basic intuitions a person has. You do not get something for nothing. The books must balance. The bill comes due. Tryon's idea says, gently, perhaps not. Perhaps the books do balance, but they balance at zero. Perhaps the universe costs nothing, because its vast positive energy and its vast negative energy cancel, exactly, completely, leaving a total of nothing at all. And if the universe costs nothing, then the deepest version of our intuition quietly comes apart. A thing that costs nothing does not need a source, because there is no debt to be paid. It does not need a reason, in the sense of something to balance it against, because it balances against nothing. Existence, in this picture, did not have to be afforded. The universe is the free flicker of a restless vacuum, a fluctuation like any other, except that this one happened to sum to zero, and so, instead of vanishing, it stayed. It is still here. It became everything, and it never had to be paid for. This is the third and deepest emotional turn of our journey, and I want to name it plainly. The universe, and you within it, may owe nothing. Not in a bleak way, in a strange, vast, almost weightless way. The thing you have always assumed must be true, that all of this must somehow be accounted for, may simply not be true. Hold that not as a loss, but as a kind of immense quiet. The universe may be a thing that simply happened, cost-free, and never needed to justify itself to anyone. Nothing, we said back in part 5, is something, and now that strange little sentence has grown all the way up. The something that nothing turned out to be is, perhaps, this. Everything, the whole universe, drawn out of the humming vacuum at no cost. But before you let that settle too comfortably, I have to be honest with you about what this idea does and does not say, because there is a catch, and we will face it squarely before the end. Tryon's universe comes from the quantum vacuum, but the quantum vacuum is not nothing. We will return to that. First, though, we follow the quantum thread to the only place we have not yet taken it, to the end of time. Part 11. The same rule, unmaking the cosmos. We have watched the uncertainty principle light the stars and seed the galaxies, and perhaps even kindle the universe itself. It has been all through this video, a force of creation. But the same rule that builds the cosmos also takes it apart. To see the whole shape of the thing, we have to follow the quantum thread all the way to the end of time. And the end of time is a long, slow, quiet place. It begins with the stars running out. Star formation in the universe is already past its peak. Half of all the stars that will ever exist were made in the first few billion years, in a great early blaze of creation. Across the 9 billion years since, the universe has made most of the rest more slowly. And the universe's ability to make new stars is steadily fading. Only the final 5% of all the stars there will ever be are still waiting to be born. The age of starlight is, in cosmic terms, gently drawing toward its close. Stars do not last forever. The most massive ones burn out in mere millions of years. Stars like our Sun last billions. And the smallest, faintest stars, the dim red dwarfs, are so frugal with their fuel that they can smoulder on for tens of trillions of years. But even they, in the end, go out. And when the last star has finally cooled, the universe is left with the dead remnants, the dark cinders, slowly leaking the last of their heat into a darkening cosmos. Now, here is where you would expect gravity to win completely. A dead star has no more nuclear fire burning in its core, no outward push to resist the inward crush of its own gravity. And gravity never stops. Gravity keeps squeezing, always, patiently. So, you might expect a dead star to simply be crushed by its own weight, squeezed down and down into nothing. But something stops it. And that something, once again, is the uncertainty principle. As gravity squeezes a dead star, it forces the electrons inside it into a smaller and smaller space. And we have seen, all the way back in Part 5, what the uncertainty principle does when you confine a particle to a small space. If you pin down where an electron is, its speed must become wildly uncertain. So, as gravity crowds the electrons tighter, their speeds are forced to spread out, to become more and more violently uncertain. And those uncertain, jittering electrons push back. They resist being crowded. This quantum resistance has a name. It is called degeneracy pressure. And it is not the pressure of heat. A dead star is cold. It is a pressure that comes purely from the uncertainty principle, purely from the refusal of confined particles to hold still. And it is strong enough to stand against gravity and hold the dead star up indefinitely in the dark, so the dead stars do not collapse. They sit there, cold and quiet, held up by quantum mechanics, by the same restless uncertainty that once lit them. For an almost unthinkable span of time, they simply endure. And I want you to notice the quiet beauty of that, because it is easy to rush past. The uncertainty principle, the rule that started as a strange fact about not being able to pin down an electron, is, at the end of time, the only thing standing between a dead star and total collapse. It is acting as a kind of pressure, a refusal, a held line in the dark. The same rule that lit the star at the beginning of its life is now, billions of years after the light has gone out, the only reason the star still exists at all. There is something almost tender about it. The universe lights its stars with the uncertainty principle, and then, when the light is gone, it uses the very same rule to keep the cold remains from falling into nothing. Creation and preservation, the lighting and the holding, both done with the same single law. But perhaps not forever. There is a deeper question about the stability of matter itself. The protons inside ordinary atoms seem completely permanent, but some physicists suspect they are not. They suspect that on timescales beyond all imagining, timescales of perhaps 10 followed by 36 zeros of years, even protons may slowly decay, crumbling into simpler particles. And if that is so, then in that unfathomable future, the matter of the dead stars would, very gradually, melt away, dissolving into a thin drift of particles and radiation. The cinders themselves would be gone, and then, at last, only black holes would remain. And surely a black hole, of all things, is permanent. A black hole is a place where gravity has won so completely that not even light can climb out. What could possibly threaten it? The quantum vacuum could. And the man who saw this was Stephen Hawking. Hawking realized that the restless humming of the quantum vacuum spells the end even of black holes. Remember that the vacuum is full of virtual particles, constantly appearing in pairs and vanishing again. Picture this happening right at the edge of a black hole, right at the event horizon, the boundary of no return. A pair of virtual particles flickers into being there, and the event horizon, that sharp dividing line between the outside and the point of no escape, can split the pair. One of the pair falls in, across the horizon, lost forever, and the other is left outside, with its partner gone, unable to vanish back into the vacuum the way it normally would. It has nothing left to recombine with, and so, stranded, it becomes real. It becomes an actual particle, and it drifts away from the black hole, carrying energy with it. Particle by particle, this slow leak carries energy away from the black hole, and, as it loses energy, the black hole very, very slowly shrinks. We call that leak Hawking radiation. Over spans of time that dwarf everything we have discussed, even the longest-lived black holes will, by this quantum trickle, evaporate. They will dwindle and fade until they too are gone, and then the story is over. The stars are dead. The matter has decayed. The black holes have evaporated, and the universe drifts on as a thin, cold, formless haze expanding into the dark. It is worth being honest about how that ending feels, because it can feel bleak, and there is no use pretending otherwise. A universe that ends not in a bang, but in a slow, cold, featureless fade is not the ending most people would have written. But notice what that fade actually is. When you look at it closely, the far future of the universe is a thin, cold haze, almost empty, almost without structure. It is, in other words, very nearly a vacuum. And a vacuum, as we have learned through this entire video, is not truly empty. It still has the quantum fields running through it. It still hums. The uncertainty principle still operates inside it. The far future of the cosmos is not the true nothing. It is the restless something we started with, spread very thin. And whether that quiet, humming, almost empty state is genuinely an ending, or whether it is simply a vacuum, waiting, is a question we are not equipped to answer. The universe may end the way it began, in a humming nothing that is not nothing at all. Now hold the whole shape of it in your mind, beginning to end. The uncertainty principle, that single strange rule, lit the first stars by letting nuclei tunnel together. It seeded the galaxies by freezing its own jitter into the fabric of space. It may have struck the entire universe into being as a zero-energy flicker of the vacuum, and now we see it at the far end of time, holding the dead stars up against gravity and then dismantling the last black holes particle by patient particle. The same rule at both ends. The rule that made the cosmos is the rule that unmakes it. Creation and dissolution, written in the same quiet handwriting. There is something almost peaceful in that symmetry. The universe is bracketed, opened and closed by the same law, the same handwriting at both ends of the book. And there is a kind of comfort available in that if you want it. The cosmos is not a chaos of unrelated rules, one law for birth and a different law for death. It is, beginning to end, the working out of a single quiet principle. Whatever else is uncertain, the universe is, in this one respect, coherent. It makes sense as a whole. It is one story told in one voice from the first flicker to the last evaporating black hole. And yet, even now, with the quantum thread traced from end to end, we have not actually answered the question we started with. We have learned a tremendous amount. We have watched quantum mechanics light the stars and forge the elements and seed the galaxies and perhaps strike the universe itself into being, and then, at the far end, hold the cinders up and dismantle the black holes. But notice, we have always been working inside the universe, with the universe's laws already running. We have one honest thing left to face, and it is the question of whether any of this truly answers where the universe came from, or whether we have only walked very carefully and very far, all the way up to a door that will not open. Part 12. The Locked Door. We have come a long way together. We began with a simple, impossible request to imagine nothing, and we found we could not do it. And now, at the end, I have to tell you something that may sound like a strange admission after 2 hours of physics. Physics cannot quite do it either. Let me be very careful and very honest here, because this is the most important distinction in the entire video, and it is the one most often blurred. We have learned something genuinely profound. We have learned that in our quantum universe, it is possible to draw something out of what looks like nothing. The quantum vacuum can produce particles. Frozen quantum fluctuations can seed galaxies. And, if Tryon is right, and the books of the universe truly balance to zero, the entire cosmos can emerge as a vacuum fluctuation that costs nothing and therefore can endure. That is a real and astonishing piece of understanding. It deserves every bit of the wonder you have felt. But look closely at the word nothing in all of those sentences, and you will see the catch. The nothing that produces particles, the nothing that seeds galaxies, the nothing the universe may have flickered out of, is the quantum vacuum. And the quantum vacuum is not truly nothing. The quantum vacuum is a something. It is a something with quantum fields running through it. It is a something where the laws of physics already hold. It is a something where the uncertainty principle is already in force, already doing its restless work. The quantum vacuum has rules. It has structure. It has the deep machinery of quantum mechanics already up and running. It is the emptiest something we know of, but it is still, unmistakably, a something. So when we say the universe came from nothing, what we have actually shown is that the universe can come from a quantum vacuum, and that immediately pushes the question one step back, and the step back lands us in the dark. Where did the quantum vacuum come from? Where did the quantum fields come from? Where did the laws themselves come from? The very laws that allow a vacuum to fluctuate. What lit the rules? Take it all the way down. Try, one more time, to think of the true nothing, the one from the very first minutes of this video. Not a vacuum, because a vacuum has fields and laws. The real nothing. No space, no time, no fields, no quantum mechanics, no uncertainty principle, no rules at all, because rules are themselves a kind of something. What could happen inside that? What could emerge from a nothing so complete that it does not even contain the laws that would let anything emerge? And here we reach it, the locked door, because the honest answer is that this question lies beyond the borders of science. Our physics, all of it, every theory and every equation, is a description of how things behave given the laws. Physics presupposes the laws. It cannot stand outside them and ask where they came from, any more than you can use a map to ask where map-making came from. A true nothing, a nothing prior even to the laws of physics, is not a place our science knows how to reach. We can describe how something comes from a quantum vacuum. We cannot say what, if anything, comes from a true nothing, because the moment we try, we have no laws left to reason with. This is why a complete answer to our question may have to wait for a deeper theory than any we now possess. For a century, Physicists have been searching for what is sometimes called a theory of everything, a single framework that would finally unite quantum mechanics with Einstein's gravity. The two great theories, as they stand, do not get along. Quantum mechanics rules the small with breathtaking precision. General relativity rules gravity with equal precision, precise enough that the navigation system in your phone depends on it. Both are magnificently confirmed, and their mathematics flatly refuse to work together. They are like two perfect maps of the same country, drawn in two languages that share no words. Every attempt to combine them, and there have been many, from strings vibrating in many extra dimensions, to space woven from tiny loops, to the idea that we are membranes floating in an 11-dimensional sea, remains unfinished, untested, a beautiful guess, waiting for evidence that has not come. And the search has a long and humbling history. Back in 1958, there was a moment of real excitement when a rumor spread that Heisenberg himself, the man from the island, together with Wolfgang Pauli, had finally cracked it, had finally found the unified theory. Pauli was invited to present it at Columbia University, and physicists travelled to hear what was billed as a triumph. But as the lecture unfolded, the room slowly understood that the idea did not work, that it could not be right. The physicist Freeman Dyson, who was there, said afterward that it was like watching the death of a noble animal. Einstein, too, spent his final decades on the problem, attempt after attempt, and died in 1955 without solving it, writing with rueful honesty that most of his intellectual offspring ended up very young in the graveyard of disappointed hopes. The greatest minds in the history of the field have walked up to this door. None of them have opened it. If that deeper theory is ever found, it may finally let us look at the moment of the beginning without the mathematics breaking down. It may open the locked door, and nobody knows what we would see on the other side. Perhaps we would find that our universe was begotten from a previous one bead on an endless string. Perhaps we would find ourselves one universe among countless others, lost somewhere in a vast multiverse. Or perhaps we would pull the door open and find ourselves staring into a true abyss, and learn that our universe really is an aberration, a random flicker, our entire existence, little more than a quantum dream against a backdrop of unending, lawless nothing. We do not know, and I want to leave you, not with a false certainty, but with that not knowing held the right way. Think back, before we close, to the cup of coffee. Right at the start, in the third part of this video, the cup was our emblem of common sense. It sat on the table, calm and definite, and it was the proof that the world was solid and dependable, the witness that stood against all this quantum strangeness. The cup stays on the table, we said, every single time, and that is how we know the universe behaves itself. The cup is still on the table. It still stays. Nothing about that has changed. But you cannot see it the same way anymore, and that is the whole journey in a single image. You now know that the cup is held there by a world of probabilities, not certainties. You know it is made of atoms that have no definite paths, swimming in their own quiet haze. You know the empty space around it, and inside it is humming with virtual particles. You know the warmth of the coffee was poured, ultimately, from a star that shines only through a quantum loophole, and that the atoms of the cup were forged in another star and flung across the galaxy by ghost particles. The cup did not change. You did. The same calm object that once proved the world was ordinary now proves the opposite, that the ordinary is built, every inch of it, out of the strange. That is what understanding the universe does. It does not replace the world. It leaves everything exactly where it was and quietly changes what you see. Here, then, is what we can say for sure. Whatever the universe came from, it produced this. It produced stars and the long, slow forging of carbon and oxygen and iron. It produced galaxies, grown from the frozen jitter of the vacuum. It produced a cold, rocky world, warmed by a star that burns through a quantum loophole. And on that world it produced you, a small arrangement of stardust, complex enough to lie quietly in the dark and wonder where it all came from. That wondering is real. Whatever its source, it is happening. So, go back, one last time, to where we started. Try to think of nothing. You still cannot picture it. And now you know that physics, for all its power, cannot quite reach it either. You and the whole of science are standing at the same locked door, in the same patient dark, holding the same question that the oldest stories left unanswered. But you are standing there, having understood something the old stories could not. You know now that nothing is stranger than it sounds. You know that empty space hums, that the vacuum is never still, that something can be drawn from almost nothing, and that perhaps the entire universe is a flicker that cost nothing at all. You have not been handed the final answer. There may not be one for a very long time. What you have been handed is a far deeper and more wonderful version of the question. And that, on a quiet night like this one, is enough. Rest with it. The door is still there, and the wondering goes on.